Alrighty, so let's talk about what you did last time, and what we're talking about in general. Oops, okay, get rid of anyway. So last time I talked to you about calculus. First, what is math?
Language.
Math is a language, and calculus is the study of change. And specifically, what is changing? What did you study in pre-calculus? That's it. So we're specifically looking at how functions are changing. Okay. There are two ways that a function can change. There's the average rate of change, so what we did last time. And how many points do you need to find the average rate of change? You need a beginning point and an end point, in this case, A or B. And when you find the average rate of change, it's going to end up being between those 2 points, it's going to be the slope of the line. You know how to find the slope of the line between 2 points? It's pretty good, right? All right. You can, one general way of writing it, the slope of the tangent line, by the way, I'm saving all of this, and it's being taped, so you don't have to write anything down. The slope is equal to the change in y over the change in x when you have 2 points. So you can evaluate the function at the end points, b and a, and then divide it by the change in b minus a. And this is one general way of writing it. If last time you did a regression with data and I asked you to evaluate it, the regression at 2 points, and find the average rate of change between those 2 points. Okay. There's another rate of change. Okay, so we were talking about the trip to Florida. On my trip to Florida, the average rate of change is when I say something like, on average, I traveled 50 miles per hour on my trip to Florida. You understand? So I did 1,000 miles in 20 hours. That's an average of 50 miles an hour. Okay? The instantaneous rate of change, what do you think that means? The word instant.
It means at one time.
At a very specific point in time. And if it's a point in time, how many points do you need for a single point in time? 1 point. So the instantaneous rate of change, which is the speed or the rate of change at a moment, 1 point. So here's the thing. That means we want the slope of the line at a single point. And what might the slope of a line at a single point look like? Well, if you take here's 2 points right here. Let me just I'll use my little handy dandy arrow point. See this right here? That's the slope of the secant line or the average rate of change. Okay? So that if I were going from here to Florida and I did 50 miles per hour, then that wouldn't be very precise. If then I said I went from here to Georgia in 60 miles per hour, then maybe I was dawdling in Florida. Oh, it was warm, it was nice, I wasn't traveling so fast. Okay? And then maybe my average rate of change in New Jersey was 70 miles per hour because I wanted to get out, and yes, I was speeding, sorry. But if I want the instant that I left the driveway, you see how these are getting closer and closer to what might have been my instantaneous rate of change. The closer I get, I must be getting closer. If I want to know what it is at exactly this point, I just have to keep moving my B and A, my beginning and end points, closer and closer together. So if I leave my driveway and 1 second later I've traveled 100 miles per hour, then I'm traveling very fast at that instant. And you would guess that I'm traveling. You would be like, you wouldn't expect my average rate of change to be like 50 miles per hour if I go 100 miles per hour in a short period. Like that's the most accurate. So if you take a shorter window, you get a better picture of what is really happening at an instant. So what we have to do in calculus, though, is since we're doing the change in y over the change in x, if we let these 2 points, so oops, I got to do another one. So I started with a big one and I got closer and closer and closer and closer. What is, if I bring these in close together to the point where they're the same point, what's the change in x value going to be at the same point?
Nothing.
The x values are not changing, but the same x value. What happens when you take the same x value and you subtract itself from itself? What do you get?
0.
And so you're dividing by what? 0. And what happens when you divide by 0?
You get 0.
You don't know what happens when you divide by 0. Okay? Well, it turns out things happen when you divide by 0. Like, let me just remind you, in pre-calculus, I'll just add this extra page. If you have something like this, okay, and that's a function, let's just call it a function, and you evaluate it at 4, what do you get? You get 0 over 0, which is what? Well, you don't know what it is. It's undefined. Okay? But what is x minus 4 over x minus 4 as a number in general?
1.
It's 1. So if you were to graph this function, it just looks like that. It just looks like y equals 1, except what happens at 4? At 4, it's undefined. So you put a hole there. Put a hole there. And we talked about that last semester. We had pre-calculus, we have functions that have holes in them. And they have holes very specifically because one of the zeros of the numerator was equal to a 0 of the denominator, and when they cancel out, they make that point impossible to be. Okay? It doesn't exist there. It's undefined. But you know what it would be if you could, like, look, if I'm giving everybody $1, $1, and just because I'm mad at Yvette and I don't give her $1, if I weren't mad at her, you could pretty much guess how much money I'm going to give her. How much money do you think I'm going to give her if I'm giving everybody else $1 except Yvette because I'm mad at her? $1. If I weren't mad at her, I'd give her $1. That's, you understand what I'm saying? That's sort of what the limit is. The limit is like, if you could, what would it be? Okay, and as long as you've got some function where you're pointing to an empty hole, it's really easy. If you're pointing to a vertical asymptote, that's not so easy. It could be infinity, or it could be minus infinity, but holes, by the fact that there's a hole, I mean, you know that when I got out of my car, you know I had an instantaneous speed because I saw it on my speedometer. So you know it exists. So just because the average rate of change doesn't make sense doesn't mean the instantaneous rate of change won't. And it will make sense because things like this happen. Like dividing by 0 in the denominator is okay as long as you're dividing by 0 in the numerator also. I mean, the numerator is also 0. Okay, so this is what I'm saying here. Delta x equals 0. You're dividing by 0. Everyone's sad. So we invented this thing called a limit. Okay, and that we invented this thing called a limit so that we could do this. So we can divide by 0 in the case of a limit because we're not actually plugging in 0. We're saying, what would it be if you could get close enough? Really, we know something exists there, but we can't put our finger on it. But, it must be something. All right, so we invented. So limit is an invention of mathematicians. Okay, and we designed it specifically so we could take the two endpoints of the average rate of change and bring them into one. That's why we invented it. And once we invent something, we can't help but jerk you around. So that's what we're going to do. But before we do that, I want to go back to, I want you to go back to your project. And I'm going to show you how you can find the instantaneous rate of change on the calculator. Okay. So you can do, last time we did this regression, so you all have your data. Are you all happy with your data? I mean, I got stuff in the mail. Let me just pause this. Okay. So what we did last time it was just, you did a regression, you collected data from your groups, and hopefully you like the data because we'll just keep working with that data for the rest of the semester. And what I want you to do today is to actually do two different regressions. I want you to do a quartic regression and, let's say, cubic regression. Okay, do you all understand what a quartic and a cubic regression are?
No.
Quartic. Quartic regression is a polynomial of degree 4. And if you look at this graph right here, I've plotted some data. These little dots here are data points, and this right here is a quartic regression. It looks like it has 4 faces. You see, it has downward behavior. It's a sad parabola. But it comes up, then it goes down, then it goes up, then it goes down. And it has maybe 2 relative maximums and a minimum, or maybe not. Maybe this is a jig where it's not actually doing anything. Okay, so there's one regression. If you do a cubic regression, that could be like this one has 3 faces, the red one. Could be like a cubic. So I want you to put in your calculator for Y1 and Y2, 2 different regressions. Let me see if I have data in my calculator. You could almost follow me if you wanted to. Stat, edit. Okay, I have data in my calculator. I don't know what it is. It's somebody's data. You only need 5 data points. So maybe this is, let me cut it down to 5 for you. 1, 2, 3, 4, 5. Okay, this is one of my, let's say how much Lady Gaga was worth in millions of dollars, because she's awesome. Okay, so maybe I'm just lying. I hope she never watches my videos. Okay, so, oops, I just lost it. Okay, so I have 5 data points in there. So I'll go in here and I'll hit stat, and I'll go over to calc, and I'll do a quartic regression. That's number 7. And I'll hit my calculator. I have to hit enter, enter, enter a bunch of times, but some of you just have to hit enter once. So it just did the regression. So now I want to put that in the calculator. So go y equals. Let me clear out all the crap that's in here. I'm sorry, yours should not be full of stuff. Okay, this is all review from what I did last time. And I told you we're going to do it every single time, so you might as well get used to it. So in order to copy that last regression that I just did into the calculator, does anyone remember the command, the mantra? Starts with vars, 5, arrow 2 to the right, and it's a regression equation, but yes. And you see it copied it into my calculator for me. So I don't even have to look at it. So that is the quartic regression. Now I want to do the cubic regression. So I have to start all over again. I hit stat, calc, and I ask for the cubic regression. So I got on here and I do cubic regression. And I hit enter, 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 enter. And now I have the cubic regression, and I want to put that in for Y2 because I want both regressions at the same time. People like choices. So there's a quartic. Now I want to do the cubic. So I'll do the same exact thing I just did. What's the mantra? Bars 5, arrow over twice, enter. And it copied it in. See, now I have a cubic and a quartic in there. And if I go up to the top and I highlight this word plot, that will ensure that I see the dots of the data points. Okay, so now if I see the plots of the data points on, when I hit zoom and I get zoom stat, which is 9, it will give me a beautiful graph. There's my data points. Look at that quartic regression. Isn't that pretty? Okay, if this is Lady Gaga's revenue, she went up. That was the release of her Bad Romance album, and this is maybe recently. Okay, and the quartic and the cubic look very similar here. Okay, they don't. If I change the window so I see more years like that, oh, that's up to 2014. She hasn't been doing much lately. Wait till she does the inauguration for the president. This is going to look very different. See, the quartic regression, I made the window bigger so I could see more of what's going to happen. What's going to happen in the, oh, they're going to be about the same, aren't they? That looks like a cubic already. The quartic probably comes down much later. The cubic is just going to keep going up. So the cubic will just keep going up, but the quartic will come down. Okay? Is everyone with me on that? That's just a little review on how to put them in there. So I need you to have 2 regressions in your calculator because we're going to do something with them. Okay? Just some more stuff that you can get from the calculator. So there's vars 5, arrow twice, enter. All right, I don't need that. This is an interesting way of finding out that instantaneous rate of change, but I'm not going to do that. I'm not interested in this at the moment. So let's just forget about this. But this right here, n-deriv, your calculator, n-deriv, can actually tell you what the instantaneous rate of change is by you just asking for the n-deriv. And if you put it in the calculator as n-deriv y1 comma x, you put that in for y4, then y4 will actually tell you what the instantaneous rate of change is. So let's see, I'm going to do that. I'm going to do that because it's easier than the other ones. So I'm going to go in here, and I'm not going to put it in for y5. I'm going to put it in for y3. Everyone okay with that? So to put n-deriv in, I go to math, and it's 8. Okay. That doesn't look the same because this calculator has been updated. So if you have the old calculator, you put the y1 to get y1. Does anyone remember how you get y1 for the calculator? It's in bars for variables. You arrow over once to y variables, and you put function y1 in. So that's where the y1 goes in this case. In the other case, it would say n-deriv y1, and then you put comma x. And here you just put x's in with the other boxes. So we'll go over here and put another x in. We will understand this notation much better later on. I'm totally, you know what? I hope you don't mind, but I'm one of these people who likes to spoil the end of books. Like Voldemort dies in the end of that Harry Potter series. No. Or maybe you know that the vampire wins over the werewolf in Twilight. Yes, I'm a spoiler. I really can't read a book unless I read the last few pages to know how it ends. And I won't watch a series unless they're all out. Like I won't go to watch a movie. I have not seen the Star Wars thing yet because I want them all done. And every time I know, well then I'm not going to watch them until they're all out. I hate waiting for things. But anyway, so I'm spoiling the end. I'm giving you, finding the instantaneous rate of change is huge, and it usually takes us about a month to get there, but I'm just telling you how to do it on the calculator right away. So you should never have a problem finding the instantaneous rate of change. Okay, so I've got it in the calculator. You have to put x's in both the other boxes. Okay. So let me go back to my notes for a second. I'm gonna capture this and put it in. Oh crap. Okay, here we go. So I'm gonna put this here so you can see what it looks like when I do it this way. Okay. So, all right. The other thing I'm gonna do, this is very cool, you should know this, but you probably don't. In the calculator, there's this thing called table setup right here. It's second window. And if I go into second window, I see this thing. And see, mine's already set for auto and ask, but if you've never used it before, it's going to be auto. And when it's auto, it starts at whatever this number is, 0, and it changes by 1. Okay? But mine is set to auto ask or ask auto, which means that I get to pick the x variable, whatever I want it to be. The table will come up the way I want it to be. So now when I go second graph, which is table, it should be empty. Oh, it's full of stuff because somebody's been in here. Uh-oh. Did I lose my? I did. So here, hold on. Delete. Is it delete clear? All right, hold on. Somehow I got to get these out of here. Delete should work. Why didn't it work before? Delete.
If you go to the top of the column on the X, maybe it'll get it.
But why is it jerking me around like this? It's dancing like it's nobody's business. Okay. Up here, if I go all the way to the top.
It doesn't look like it's going to work. So.
Delete. Go away. See, on my table, it's going away. Yours won't do that if you have it on auto. Did anyone try it on auto? Anyway, I can type in any number I want. So 2015, Lady Gaga's worth in 2015, this y1 was the cubic regression. No, it was the quartic regression. And y2 was the cubic regression. Which one says Lady Gaga's going to be worth more next year? Next year. That's 2015. What planet am I living on? How about 2018 is next year? Which one's worth more? Which one says she's worth more? The cubic or the... Yeah, the cubic one is like really loving her. She's the best. In 2025, you know who, when your kids are listening to Lady Gaga? The cubic is like, yeah, she rocks. And the quartic is like, it's done. Your kids won't listen to her. Forget about it. Okay. Now, what does this tell you? This right here tells you how fast this is changing. So in 2015, when Lady Gaga was worth 6807, her value is going up. And this is the rate at which it's going up. It's going up about $600 million a year. Good for her. In 2018, it's going up even faster, according to the quartic regression. In 2025, it's plummeting. Okay? So these are values, and this is a rate. These are how much is she worth? How much is she worth? This is how fast the first one is changing. Are you with me on that? So the calculator will calculate and tell you very cool things. So you can answer that question also. Okay. So in this case, here's an example where this is the derivative. This is a very simple one where it says at $91, the revenue is $15.07, but it is decreasing by $1.40 a dollar. Okay, so that's how you would read that. If this is if y2, this must be the derivative of y1. Okay. Are we good with that? All right. So if you look at this, if you look at the slope of the tangent line, you can get an idea of what it's supposed to be. Here it's either 0 or decreasing. I mean, if it's a maximum, let me just draw some tangent lines here. I'll draw them in red. Okay, tangent lines at maximums are 0. And I said it's top, it's 0. If there's another 0 here, like I don't know what's going on here. I don't think, it's just the calculator's not drawing it well. But it's probably going down. Okay. But you know what would tell us? If we put this in the table, we look in the table, it would say it's negative. Then we would know it's going down. Okay. Anything else on here? That's just evaluating it. Okay, so now this is what some of the groups did in the past. This is what I want you to do. And I want you to think about this is what I want. So let's do this now in our groups. And this is what I want. Look, I want 4 things. Maybe I should tell you this. In pre-calculus is the study of functions. What are the 4 ways we can represent a function? Data. So I need to see all your data. It makes me happy to see data. A graph. And just take a picture. I would take a picture of this from the calculator if you can. And an equation. I would like to see an equation. There's no equations here. So write down whatever the regression equation is, I would like to see it. Just, you know, whatever it is, it's like, you know, 1.2 ... x squared. You can just use dots if you want. But give me enough, give me the equation. And then I'd like to see, when you evaluate, this should be the regression equation right here. I want to see a regression equation and I want to see a derivative. And I just want to see it at one value. Just pick a value like that's relevant, like next year. And then the last way you can just represent a function, so it's data, graphs, equations. The last way you could do it is in words. And I want you to say in words what it is that you've accomplished. Like from the age of 90, the rate of cancer is decreasing by whatever, 1.76. Okay, it's very persuasive if you have all those things. If you have your data, your graph, your equation. Okay. I want to tell you about this, and the numbers are going to be kind of ugly, so don't feel compelled. I mean, you can take a picture of them, however you want to do it. Here's another group. I'm going to ask all of you to make a statement and tell me how fast it's changing. Okay, because that's really what we want to know. Okay. All right. Let's try that now and see what we can do.